have talked about theoretical full bridge DC-DC converter and its template based design based on PE Expert and PE Mag tool. Now let us try to understand how the actual design can be implemented. So I'm showing one of the image from ST Microelectronics, and this is a company which generates or which provides a solution for gate driver, gate protection, current sensor and control unit ICs, and even MOSFET devices as well. So this is a semiconductor manufacturing company, and they provide the solution for EV DC-DC converter. So what you see over here is a high voltage battery pack, and its positive is connected to the primary side of a bridge and its negative is connected like ground over here. The gate pulses are generated from a microcontroller unit, and this gate pulses will be given to the gate driver, and this gate driver will provide 4 different pulses to this MOSFETs, and there will be a sensing as well in order to determine what is happening with the output and input and with reference to voltage and current. On the secondary side, what you have is a synchronous rectification where this MOSFET will conduct from actually source to drain in the top direction. So this LV battery will get charged and this current will be flowing in this direction. So let's say this is the positive part, and from which the current will be flowing like this in this direction, and the current can actually flow in the top direction from the switch, and whenever the battery is discharging, this can be reversed. So whenever the battery is discharging, the current through the MOSFET can be flowing down from top to bottom. So there are gate drivers and protection required for the secondary side, and there will be an isolation as well for sensing, and there has to be a signal conditioning circuits as well. And let's say this is the LV battery, which is 48 volt or 12 volt battery, and this converter together with primary and secondary power switches along with the transformer can act as a fully bidirectional converter. For a fully bidirectional converter, probably you need more number of switches for a battery control. So secondary side, instead of diodes, the MOSFETs are used, and it is known as a synchronous rectification. So the modifications are required for a bidirectional power flow. So now we are going to actually have a look at the entire design which is suitable for a battery charger from 400 volt bus. So we are going to see this design example, and here we have 400 volt input side and 36 to 60 volt, or we can say 48 volt nominal output side, and this is constructed using 4 MOSFETs on the primary side of a transformer and 4 MOSFETs on the secondary side of a transformer, along with a clamp MOSFET and the capacitor. So this is a particular design which will do the bidirectional power flow. So the power can flow from high voltage to low voltage in this direction, or it can flow from low voltage 48 volt to 400 volt in this direction. And this is such a design which can actually be built for an EV application as well. So the reference is bidirectional DC-DC converter reference design with this number, and you can actually study the entire design and its working in the documents available on the Texas Instruments website. So what we are going to do with this design, we are going to use this PCB design files, and those PCB design files we can include these files in the SI Wave, which is signal integrity tool from the Ansys, and we can analyze the overall output or overall performance of the PCB under a certain situation. So this is the image of the actual board, and what you are able to see in this image some power switches which are mounted on this big heat sinks. So there are 4 power switches, let's say, on this heat sink, another 4 power switches on this heat sink, and this is the yellow color is a high frequency transformer. So this is an actual image of the power converter board, and this power converter board can actually supply 2 kilowatt of load. So this is the image of an actual prototype built by Texas Instruments, and we are now going to do the PCB design analysis or electrothermal design of this PCB, which is used for full bridge DC-DC converter. And this is a typical design example of 400 volt to 48 volt, and which is very much similar to the requirements of an electric or hybrid electric vehicle. So let us go into this design example. I'm going to show you some PDF files for this design example, and then quickly we will go to Ansys SI Wave, and in that tool we will analyze this printed circuit board. So over here, let's say we will be analyzing this printed circuit board, and we will be able to do the fundamental signal integrity and power integrity analysis. So what I am showing you here is the fundamental layout of the printed circuit board, and what we see as a circuit and what we see as a schematic are completely different, because we have to include all the involved components over here. So for example, on the high voltage side, you have this gate driver circuits like UCC21520 for each leg, and for each leg this is going to be another design or another add-on cards. So similarly over here we have another add-on card which is TIDA01141, which is for sensing the current, and here you have a control card which is TIDA01281. And what we are going to focus on is the power stage architecture. We are going to see the PCB for the power stage. So if I scroll down through the schematic, these are the components, and this is how the entire schematic is developed. So what you are able to see are these are the 2 top MOSFETs and the bottom MOSFETs. They are connected with the input side of the transformer T2, and here on the secondary side you have again combination of top 2 MOSFETs over here and the bottom 2 MOSFETs over here, along with a third switch. So what we have as a power architecture, these are all FETs along with the transformer, and these 2 are the input terminals where we can see over here, and these 2 are the output terminals, and we are going to see this architecture in the PCB as well. If I show you the PCB layout of this, so what we are able to see in this PCB layout is, on one side you have this 4 switches mounted. So these are the 4 MOSFETs along with the heatsink. So the heatsink is through long like covering entire all 4 switches over here, and there are another 4 or +1 switches over here, and this is the main area for transformer T2, which is the main transformer. And here you have big capacitors on the input side. These are the 2 capacitors on the output side. So this is the overall power architecture of the design. So if I show you the layout of top layer and the bottom layer, so this is something the PCB design will look like this, and this is what we are going to import into SI Wave. So let us start with Ansys SI Wave and import our PCB design, and I'm going to open Ansys SI Wave. So basically the SI Wave stands for Signal Integrity Wave, and it is a tool from the Ansys in order to perform power integrity and signal integrity. So this is the window of SI wave. This is how it will look like, and what you can see in the middle is the area where you can see the PCB design. So you can see the PCB design over here, and it will be possible for you to include the PCB over here. So what you need to do, you need to translate your PCB design files into the format which are supported over here. So with the help of Altium Designer 20 software, I translated the design files into IPC 2581 standard. Basically these are the export file for the manufacturer. So when you export those PCB design files into IPC 2581, you will be able to import them over here. So let me open this project and let us see how it looks like in the SI wave. So here is the PCB design project which we have, and as you can see, this is a two-layer design, the top layer and the bottom layer, and you can see the terminals over here. This is the transformer, these are input terminals, and here you have 4 number of switches, 1 2 3 4 and actually 5, and here you have another 4 number of switches which are through hole MOSFETs. So here these are the power devices, and this is what you can correlate with the design document. So I have imported this, and I can actually now do the analysis. Let me close this part, this, so that we are able to see the entire design, and probably now you can see design in a better way. So this is the entire board which we have imported, and it is basically 173 mm by 185 mm. And let's start DCIR analysis. Now what is DCIR? So basically we are going to do a DCIR drop analysis, and this can be done from the SL Wave workflow wizard from this option. So this is a kind of a short key over here, and through this wizard we can quickly launch a typical analysis. So we can also configure the power integrity analysis. That option is also there. So let's start with the DCIR, and as you from the name itself, it's basically the voltage drop analysis, and what will happen if you have that much level of voltage present in your board, how much current is flowing, and what will be the effect of voltage and current across the plane of a PCB. Now if you have voltage and current, and if you know the track width and the track material and the track properties, you can basically calculate how much will be the voltage drop. And if you calculate the voltage drop, which is nothing but I into R, you will be able to calculate the power loss as well. So you can from here do the complete electrothermal analysis. So let's start with the DCIR drop analysis, and in the configuration what I need to do, I need to basically select some of the nets available from the design. Let me select some of the nets. So what I'm going to do, I'm going to select high voltage ground, and I'm going to select V bus. So V bus and high voltage ground are selected like this, and I'm going to select battery positive and negative. Why I am selecting this? Basically this is from the design example. So I'm assuming that we are giving 48 volt input from the low voltage side, and we are going to get 5 ampere current on the output side, and this you can configure. And once this is done, you can basically select what are the type of the current and whether you have the voltage source or current source over here. whether you want the distributed current or the constant voltage type of current source, and you can actually add the magnitude of the current as well. So for simple analysis, just to start with, I'm giving these values. So I will click on configure simulation. So these values will be assigned to the simulation, and this simulation will be configured over here. And the next step is validation. So let us validate the design, and if I click OK with the default settings, this will validate all the connections and it will come up with a result report. So once the design is validated, we can basically start the simulation. So if you have any errors in your design, you can basically select the auto fix, and this will be done automatically. So let's say if we have all the 0 available over here, we are ready to go with the simulation. So what you can see, the stepwise DCIR configuration. So the green tick mark over here in the configuration simulation is done. We have validated the design, and now I am ready to hit the simulation button. So let's start simulation. When I am going to start the simulation, I can actually configure the tick mark for Ansys Icepak option, so that I can create Ansys Icepak project and export that power dissipation from here. And what I need to do, I need to basically select at least one ground for the node, so through which I'm going to select the 0 volt reference. So let me select this high voltage ground and click as a negative, and I'm now ready to launch the simulation. So I'm going to now launch the simulation, and you can see what is happening in the simulation manager over here. So I'm able to do the 100% setup, and simulation is also now going to finish. So this simulation gets done quickly, and here we can have some messages from the SI wave. So what happened with the simulation, and we can figure out about the results. So how to view the results? So in order to see the results, you need to click on the results window over here, and we perform a DCIR. So I need to click on DCIR and DCIR sim. So if I click on DCIR drop and do this analysis, we can actually figure out how the voltage and currents are on the power board. So on the power converter board, we are going to now plot the voltages and current. So let me select plot voltage and current, and here is where the output will look like. So let me select J, which is basically the current, and if you see the current, we can see in the power card that how the current is flowing and what is the current density. So here we have around 4.5 ampere per meter square current density for the red color, and you can see how the current is coming out from one terminal of the input 48 volt and going into this, and where else the current is flowing, and you can actually see the distribution of the current in different areas as well. So I just defined the high voltage grounds and high voltage input and output, or battery positive and battery negative, which are these two terminals. So I'm able to see over there itself. So if I have decided to choose many other connections, I could have got some value of the currents over here as well, but this is what is happening, and you can see those arrows of the current representing the current density over here. So apart from this, what we can see in the output is not only the current density, but we can choose to have the voltage as well. So let me uncheck current and check the voltage on the top layer and the bottom layer, and let's see what are the voltage levels. So as we can see, we have given the excitation input as 48 volt over here in the red color. You can see all these planes are red color, which is 48 8 volt, and the blue one is the 0 volt. So because we have considered the output as a current sink type of a load, we are able to see this. And this is just one of the possibility where we can see the output, and you can analyze actually the temperature as well. And if you have configured the Ansys Icepak, what you can do, from the result tab you can click on export Icepak power map. So you can get the details of what are the losses happening on the board and how this losses will be observed, and this can be exported into an image as well. Or if you want to see this in the simulation result itself, you can click on plot Icepak power map. So when you click on Icepak power map, you will be able to see the power levels at different part of the circuit. So these are basically the losses happening over here, and as you can see the track width, and since the PCB is very large, you see a very little amount of losses happening. But you can configure your input case and you can see in extreme conditions what are going to be the power loss in the PCB and what is going to be the temperature rise. So this is what you can do with the SI wave. And now let us switch to Ansys Icepak. So you can actually export this to Ansys Icepak, and you can open the same project and you can check on the part where whether it's possible to have circuit without cooling, right? And you can analyze the performance of PCB without any cooling or with cooling using Ansys Icepak. Ansys Icepak is basically the temperature and flow solver, and temperature and flow related simulations can be done separately in Icepak tool. SI wave over here, you can set up the electromagnetic related thing. You can select about resonant mode, you can check on the crosstalk, you can do the RLGC result, you can do the AC current, and so there are many signal integrity and power integrity related checks are possible through the SI wave. Now you may be looking at or you may have heard this signal integrity and power integrity terms very first time. So let me explain you what is the meaning of signal integrity and power integrity, and why is it very much important once the virtual design of the board is available. So let me close this. So signal integrity is basically the quality of the signal. The power integrity is basically the quality of power. So integrity itself refers to whether it is satisfying the demand or not, or whether you are getting the correct signals and correct power levels in the circuit or not. So signal integrity is a set of measures of the quality of an electrical signal, and it is very much important in case of a circuit which is communication related circuit, or in case of power converter circuits you have switching frequency of, let's say, more than 20 kilohertz, and then your signals should reach to the gate terminal of the device properly. And what happens if there are any noise? What happens if there are any kind of a disturbance added to the signal, right? So this is what you can check as a signal integrity. What is power integrity? Power integrity is another analysis to check whether the desired voltage and current are reached from source to destination. So let's say if I apply 400 volt and whether I am getting 400 volt and required current on the other side of the board or not, or how much is the voltage drop, how much is the leakage current, or what's happening actually on the board. So these two analysis can be done using Ansys SI wave. So this is the end of our demonstration with the Ansys SI wave. Now let's move on to Ansys Icepak. Now in Ansys Icepak, I'm going to show you a built-in example and we will see how Ansys Icepak can be used for power converter simulation. So I'm going to open the Ansys electronic desktop, and through which we can access the Ansys Icepak. So in the Ansys electronic desktop, what you can do, you can select the Ansys Icepak from here and insert a new design, or let's work upon the example. So I'm going to go here and open the example. We are going to run a built-in example for the Ansys Icepak. So I will go to Icepak folder and I'm going to select graphics card. So here is a PCB for a graphics card, and we are going to see the simulation of that. So what you are able to see now is the actual 3D model of a PCB along with heatsink and all other components. So these components may be some of the connectors or capacitors or the heatsink. So what you are able to see is a readily available built-in project, and what you can see in the Ansys Icepak, you have a geometry, but the purpose of the analysis is to get the temperature distribution. So here the analysis is in terms of solving the thermal and the flow simulation. So if I do this and if I check on what is the analysis setup, I can see here the problem type which we are going to solve is a temperature and the flow. So basically the Ansys Icepak is a sophisticated tool which is used for cooling, or we can say the thermal analysis of printed circuit boards or electrical and electronic item. It can be used for the case of let's say a panel or any such enclosure, right? So when you come to a mechanical design of a cooling system or thermal design of a power converter, this Ansys Icepak can be very useful. So if I go out of this, here we have created a box, and this is going to have its boundary as well, and we are going to see the simulation results of this example. So in order to get the simulation result, what we are required to do, we are required to do the analysis and select analyze all. So if I right click on analyze all and select this, it's going to take around let's say 10 to 15 minutes depending on the type of analysis which we are doing. So I already have the result available, and I can actually plot the temperature for this case. So I'm interested to plot the temperature distribution curve for the setup example. So let me open the example which I have already run, and I have saved it to my hard disk. So I'm going to close this and I will open Icepak example. So this is the same example which I saved and run earlier. So here what you are able to see is the same arrangement, and we are interested to know about how will be the temperature distribution. So let's see the temperature distribution for this graphics card. So this graphics card PCB, how to see the results? The results are available in the results section, and you can calculate the field overlays as well. So if I click on the results and if I check the solution data, these are the solution data available to us. So in terms of monitor, in terms of residual and the profile which we have set up, these are the results which we have got. So the X velocity, Y velocity and energy, these are the plots, and this is what we are getting as the output, which is the temperature, flow and the speed. So we are plotting temperature, and which is basically the red curve, and speed, which is the green part. So this is how you can analyze the results. Apart from this, you can plot the temperature field. So if I double click on the temperature, here is my temperature distribution available. So as you can see, the highest temperature is there where you have this boards, or we can say that this typical ICs. So here is the memory IC1 and the memory IC2, and these ICs are actually having most of the higher temperature, and look at the value of the temperature for this too. So it is around 75 degrees centigrade. So with the default solution setup, I simulated this, and I can decide to see some of the temperature layers, and we can see how the temperature is distributed in Ansys Icepak. So here not only you can analyze the distribution, but you can look at the animation as well, right? And you can actually set up the cooling as well. So if you have cooling from, let's say, negative X direction, right, and then this heat sink will actually cool down the major part of the board, and you can see what is happening with the board. So, and it's also possible to do the animation. It's also possible to see the results with cooling and without cooling, and this is what Ansys Icepak can provide the solution. So in case of an EV DC-DC power converter, we can actually translate our design from PCB to SI Wave, and from SI Wave we can export our design to the tools such as Ansys Icepak, and we can run the flow and the temperature simulation, and for this results can be there with cooling and without cooling. So we can also decide on how much cooling is required. And in fact, this is not the end of the design stages. So let us look at the design stages again, and let's try to understand what are the all things which we have learned. So in a typical design stage, we started with the requirement specification. We have seen PE Expert and PE Mag. We did the circuit simulation and schematic using Twin Builder and Simplorer. We have seen some of the example. We exported our PCB design output files in SI Wave and performed the analysis for DCIR drop. This Icepak, we have seen one built-in example of a graphics card. Now it is not like the end of the design phase, right? And in actual case, the engineering team will be working as with power electronic engineers along with the thermal engineers, and they may start their activity from this phase, and they just have a look at the dimensions, right? So requirements are not only in terms of voltage and current, but it can be in terms of volume of the product as well. So how much is the volume available, how much is the size available, and whether you want cooling or not. So in case the cooling is required, how this cooling will be provided. Is it going to be the air cooling or liquid cooling? And in case the losses of the power converter are going to increase, whether this much of cooling will be sufficient or not. So all this electric vehicle related simulations can be done with all different sets of Ansys electromagnetic suite tools, and they are going to be interrelated each other. So from PE Expert and PE Mag, you can actually connect your transformer in the Simplorer. From Twin Builder and the Simplorer, you can have your schematic ready, and you can do the PCB design in a PCB design tool, and those PCB design output files you can feed into the SI Wave and the Icepak, and you can check finally how is your thermal performance, how is your electrical performance. So this is how the Ansys tools can be useful for power converters. So this is the end of the course. Thank you for participating in the course.